Mm. Today we will come now we come to the last session on demonstration of a Cahn-Hilliard FFT module MicroSim. So it is solves the phase field evolution equations for uh, the same. Cahn-Hilliard equation Alan Cahn for precipitate growth or the spinodal decomposition. So I would like to give brief introduction as we are going through all the phase field lectures, so we may come across similar equations again. So here the assumption is that a precipitate is growing into the matrix phase. Right now the model is implemented for constant temperature, and so there are certain physical, model assumptions which I would like to mention, like the scaled compositions where you can use 0 and 1 for matrix and precipitate compositions, and the free energies are rescaled, and those things are incorporated into the model, and at the same time we are also able to demonstrate how a real alloy system with the input from the Gibbs energies, at least for the thermodynamic part, can be taken into account as similar to the KK's open cell module. So, and coming to the equations, same Cahn-Hilliard equation and Alan Cahn. The Cahn-Hilliard alone, we can look at the spinodal decomposition in a system where binary alloy of solutes with A and B, which decompose or spinodally decompose into AA rich and BB rich regions, and the Alan Cahn together with Cahn-Hilliard, we can couple them and study the precipitate evolution where the structure of the different phases are different. Precipitate and matrix, that can be incorporated, and this is the chemical potential which taken into account and so on from the previous discussions. I would like to skip few things, and the contribution of the free energy, the free energy functional can be similar to the previous functions, which is a contribution from the chemical part alone. The elastic contribution is not yet included in the model, and you can see the gradient energy coefficients, which contributions from the composition and the phase field, and the F is the free energy from the bulk of the system, and which has a contributions like the precipitate and the matrix. Here you can see these are the model systems, or else I would say scaled systems for a given conditions, are modeled with simple second order polynomials, parabolic functions for matrix AC square and precipitate B into 1 minus A whole square. And so these are the representative curves which shows the Gibbs energy functions, the free energy functions, and the free energy is interpolated using the interpolation function given over here. This is similar to h of I, which I have been discussing in the KK's module for the OpenCL, and then going to the combining all the Gibbs free energies, writing the entire free energy of the bulk system, which has the minima, the double well potential inclusion over here, and the contributions from the bulk phases which are interpolated through this function. The 3D plot can be overseen here with two wells, which as a function of phase field and composition. As for a representative, I'm showing this plot, and then if you change the FM and FP, so similarly you can get the values for a real system to get a visualization how it is going to change. And so these are the evolution equations I was mentioning, the final evolution equation. So especially in the case of Cahn-Hilliard, here also the scaled composition which gives rise to a free energy curve with a double well, and this can be used to study the spinodal decompositions, and we are also going to demonstrate how it is going to happen in the real system. So the physics of the spinodal has been taken care where the curvature, negative curvatures deciding and the transformations, and also taking account into the spinodal region has to be taken care when you are doing this kind of simulations. And then coming to the numerical implementation, so we have used the semi-implicit Fourier spectral method as mentioned. It is clearly discussed previously by Professor Saraswati Bhattacharya. So as a just here I'm going to see equation in a real uh, space, and the similar equation in the Fourier space, which is represented with a tilde as a variable in the Fourier space, and the k is vector by vector, and is an integer number, so that which is associated within the Fourier space. And coming in down further, so I just gave the little glimpse how it was implemented. So this is the Fourier space, the equation Fourier space, where you can see the df by d phi, which is the free energy derivative with respect to the phase field variable, which is represented as some function g, and also the gradients over here represented in the Fourier space. So we used Fourier semi-implicit scheme where the g phi is being calculated in the current time step, and the other parameters are being calculated in the future time step. We used the backward time step, and we got this the final expression. And similarly for Cahn expression, which I would like to mention that the mobility and the gradient energy coefficients, similarly the relaxation parameter and the gradient energy quotient has to be taken care the input, as mentioned in the previous simulation lectures also. And then I will go how the scheme is done directly. So we used as I mentioned, from the real space we calculate the gradients, and then we get the Fourier space values for the gradients, and then also we transform so that means we are going to transform the C and Z into the Fourier space, and we are going to update and get the updated values into the real space. So this is similarly adapted for the phase field variable also, and if it is a coupled equation, they are done together. And then we are going to see, I would like to emphasize here the concept of non-dimensionalization, because the equations at the beginning and the end are similar, as pointed out by Professor Abhig, that the input file can take any values, whether it's a dimensional value or non-dimensional value. So currently this solver can take dimensional or non-dimensional values, so which we have checked. So as we are telling, the scaling composition is carried out through this, where the precipitate composition will be represented by 1, and the matrix composition is represented by 0. So where the C prime, the prime values indicates the dimensional values, which are the equilibrium or the compositions in the precipitate and the matrix. And so through the non-dimensionalization we get the relations between different variables, chemical potential or the evolution terms and the mobility terms. So when we are accounting for this non-dimensionalization, so the final equation in the non-dimensional form is represented over here, which is also looks similar, but when we are solving, it is a matter of fact how we are going to solve, what kind of input we are going to use, whether if you are going to use non-dimensional input, we have to scale accordingly and analyze, and if you are going to give the dimensional values, so the whatever the results we are going to get in the dimensional form. So that I would like to emphasize, and so that is being represented over here, which represents various dimensional and non-dimensional conversions for time step and energy and other parameters, where we tend to take the scaling we tend to take by taking the kappa, and the mobility is being taken 1, and accordingly I will show in the demonstration how the non-dimensional values we are going to take straight away. And one more thing I would like to emphasize, that in the case of Spinodal, the double well potential, how we are going to account it for the scaled values. Here you can see the Spinodal phase diagram, within which we can see the C alpha prime, C beta prime as a composition in the phase separated regions, and this correspondingly you can see the phase diagram over here, and these compositions are we are going to get so the common tangent constructions where the chemical potentials are equal, which those compositions represents these compositions in the each phase with the matrix and the precipitate. So this is scaled accordingly according to this expression where it tends to bring the uniformity. I mean it brings the two wells at the same level, so which can be accounted with the scaled compositions. So that I would like to emphasize. So correspondingly, once we take the free energy expression, so it is going to be in the form of same AC square and 1 minus C whole square, so which looks like this for scaled Gibbs energy, sorry, scaled free energy function. So it is essentially the scaling of the variables so that you can represent the system similarly. So one I would like to mention is so the physics phenomena you can represent in any mathematical expression, so that we have to remember when we are doing these things. And you can see the similar expression which comes out for the C alpha is equal 0, C beta is equal 0, which is the two minimum at the same energy. And so this is what I was mentioning. So I quickly go forward, and so I was thought of telling a little detail about Gibbs energy descriptions. So I was had a chance to get the details shortly in the previous talk. So I thought I will emphasize a little more things over here. And as we are mentioning, so there was a clear big discussion about this traditional thermodynamic expressions being accounting for various phenomena in the phase transformations. So these expressions are accounting for classical thermodynamics, and the expressions are developed through the Calford method, which I would like to mention, is where they can be extrapolative from binary system to unary to binary, binary to ternary, and so on. So this extrapolation is works for the system. There is no new phase formation, and if there is a new phase formation, you have to account for this account for the phase, and you have to do everything from the scratch, from unary, binary, ternary again. So the idea of the CalFAD we can use. So the databases are available. So where are the systems? For example, a solid solution where the ternary or the multi-component mixing is not much important, or it is not going to play a big role, we can extrapolate and use them as a multi-component databases, but they have their own limitations. You have to carefully account for the thermodynamics or physics phenomena involved. And so these are the models, how they are going to go about it depending upon the what kind of phase, for example, fixed compositions and solutions. And these are the methodology they are going to adapt when they are developing these models. And so this expression which I have previously showed, and this Gibbs energy of the element which is can be used for extrapolative in the binary and ternary alloys. So this binary the pure element data is stored, they are standardized through SGTE, and which can be used later for assessment by different groups to develop the multi-component system. So they account for all the contributions, chemical, magnetic, and pressure. So this discussion is also there in the previous talk. And from these expressions, they tend to extrapolate to alloys where the excess contribution which comes through the non-ideal mixing, so which I have mentioned previously, I will skip. And so these are the similar parameters which account, this is example for a binary alloy, and further about the Redlich-Kister polynomials, and these are the essentially A plus B is the model parameters which are going to describe your system. And you can extend this to multi-component system. For example, if you see ternary, besides this term for binary, you can have a ternary term for a ternary system. And so these are the different expressions which are going in there, and Li, Jk over here are the parameters which are going to be used from the going to be developed through the Calford method, and which we can use in our phase field models. And you can see as we go for multi component system, the ternary interactions contribution becomes less. It depends because xi, xa, xk, we can say if you take these are the mole fractions or atom fractions of the elements, and you start multiplying. So you can say the contribution so much order by difference it reduces. So finding higher order terms is very rare, but we cannot exclude the possibility. And so one thing I would like to mention here is the sublattice formalism, where uh, uh, the uh, the sublattice formalism adopted in the Calford method, which we are better to have some idea, because when we are going to read the TDB, certain things I would like to highlight as are because if some error goes or error comes, or how to understand if a TDB file. So here are the simple liquids which are here. You can see the each parenthesis represents one sublattice in the form in the developing that model. For example, liquid, we always tend to have one sublattice which is a uniform mixture of all atoms. And the stoichiometric phases, for example, Na3Air, so where we consider the two phase ordered structures forms because of in the form of two FCCs. So those we can account over here, and substitution solutions where we tend to substitute one element by other element, that is substitutional solid solutions, where the vacancy phase remains as a vacancy, as which is nothing but a interstitial site which is going to be a vacant. And the interstitial solutions where a carbon, for example, we can account which goes to interstitial site, and iron which is in the substitution site. So those things are modeled accordingly. And the compounds. So just I would like to emphasize these are the things which are available, and you will see this method when you open a TDB file. And so which this just I would like to give a glance before going to the simulation for the TDB file. So I would like to emphasize for a new user, if they are going to use a TDB file, how it is going to happen. So this is a TDB file for FECR which is downloaded from and this website. They have a repository of thermodynamic databases and NIMS website for CPDD, and so this is assessment carried out by these people. So they tend to document the previous recordings, so that they always try to improve based upon the limitations in the previous model. So the first thing, it represents the pure elements which are going to be present in this system: iron, chromium and iron, and their crystal structure, and so on. And also it describes the pure element of Gibbs energy functions here over here with the function definitions. All we can say liquid FC, G liquid CR. For example, if you take chromium, all the three phase descriptions are available. So BCC and liquid and FCC. Though we know that chromium doesn't exist in the FCC form, but they do develop the Gibbs energy expressions to another to incompatible with all other models or all other solid solutions. And this is the liquid phase description, where you can see this term and this term. This is A plus BT form, you can see clearly, and this is also A plus BT form, but where B is equal to 0. And you can back substitute these expressions and get the Gibbs energy expression. That is how it is going to be the Gibbs energy expression if you generate it through the Python file. Here you can see that is clearly representing. So this term over here represents the how many sublattices are available. So it is the one sublattice with the full contribution from one sublattice where where chromium and iron are present. Similarly, the BCC and FCC parameters can be described. So the magnetizing also introduced in the system while modeling. So that information also you can find out over here. So this is where you can see. So this is a sigma phase model. There are three sublattices there where they represent three sublattices. So this is something you need to keep in mind when you are writing Gibbs energies functions. You have to make sure that these are taken care. We are tend to incorporate all this physics into the Gibbs energy writer, but as of now it is going to read the solved solution. In the future, the precipitate or stoichiometric phases are going to be taken care in the Python module. So with this, I would like to open the uh, our module, MicroSim GUI module, and this time I am going to import the new file, and I will explain what are the things which are going to present in the solver and what possibility is there, how we can this can be extended further. And I'm going to choose an in file which is over here. So I'll just run through these steps because it is repetitive, and we are going to give all the parameters. So here you can see this is okay, this particular simulation is for Spinodal, so that's why I gave the two same names, phase 1, phase 2, which are the Spinodal decomposition phases, and elements are also here. Further down I'll go, and number of time steps and the material parameters, and so this is BCC, both are BCC. I'm going to use the scale parameters, so it is I'm going to give diffusion as 1, here also 1, and then gamma, so these are all 1 values, material parameters, boundary condition. So this is a Fourier transform, so this is implicitly it is going to take the periodic boundary condition. So for the completion I'm going to give it the periodic boundary condition, and then, so once we start doing this, so there are certain steps which we cannot skip, so we have to give all the boundary conditions for all the system, so which will be highlighted for taken care in the future releases. And the model parameter, here we are already in the Cahn Hilliard, which is highlighted with this black outline, and we are going next. So I'm tracking progress. So the scale values, as I'm telling, the dimensional values I'm going to use. So here there are multiple options available in this interface alone. So one is the two equations are in the same solver. So one, if you want to do a Cahn Hilliard where the similar structure is evolved, we can use enable the flag accordingly, and then the phase field equation for the Allen-Cahn equation won't be solved irrespective of whether you give the parameters or not. So it will take only the information of the Cahn Hilliard. And the second is the TDB flag, whether you can enable or disable. So if you are going to disable, make sure that you are giving the values the ones the dimensional or non-dimensional. If you enable the TDB flag, try to give the dimensional values, or else similarly we can give non-dimensional values also we can give, but that need to be accounted right now. But it's better to give the dimensional values, and accordingly we can proceed further. And so this similarly the diffusion matrix here, which we mentioned over previously, here it is a atomic mobility matrix which we are also scaling to 1, and as we mentioned previously, where we can scale these values to 1 and 0, we can give the similar output. Right now this is going to be a spinodal simulation where I'm going to take only the 0.5 as my input, the entire matrix, and which is taken with added with a random, so that initial random microstructure, fluctuated microstructure is created. So this option also we can enable where the initial input can be taken from the user defined input. So that option can also be enabled. So here it is there at the end. To run the simulation, I'll run 1, I'll make it, and I'll make run 1 here also, so that we can keep track what is going on. And generate files, so I'm going to generate it in a different folder. So unlike where I had some issue in the previous solver with OpenCL, so that is slightly strict. The overhead comes with the cross platform compatibility. The overhead is there always with OpenCL, but here we can see I'm going to create one demo runs, and I'm going to choose this folder where it will. Okay, so this giving empty filling because this is one step which we cannot skip over here, because though we are using a spinodal where we want to uniformly spill, here we can give the option to user where they can import the initial microstructure which can be a random microstructure, or which can be generated through other statistical tools uh, for initial phase of microstructure. So I'll just try to add one for the sake of completing the profile over here. So this is not going to matter right now, but anyway we have to proceed further. Okay, we are in there. So generate input file where demo runs. So choose. Okay, it is filling is done and input parameters done. But as we enable this spinodal, the spinodal is going to overwrite. The flag is going to disable this filling. So that is taken care. I'm going to run. So it is running, and just to see. I hope we have written one time step which we can see. Okay, so it is kind of evolving, so we can see the 0th time step and further down. So apply. So you have to remember that the opening preview in the terminal always opens the current the last saved time step. So here is the initial microstructure which is evolving. So with this I would like to close this demonstration, and I would like to go further down where we can give the information through the TDB file. So in the Cahn-Hilliard model, we were going to give the TDB file where the TDB flags are enabled. So what I'm going to do is I'm going to import a file which reads the TDB, the input reads the TDB file enabled. But I would like to emphasize we have to create the Gibbs energy function through the Python script. Right now the Python script is not integrated in the module, but in the future it is going to be enabled. And so main so in file, so here is one in file, Spinodal open. So I think yeah, probably in the, so it is going to have the all the information and description where I have given the dimensional values of the delta x and delta t. This is 1 nanometer and this is particularly seconds. So we would like to give a try, as Professor Abhi said, whether it's a dimensional or non-dimensional. So all the input parameters matters how we are going to give. So that I'm going to demonstrate over here. The phases here we should be careful. I'm going to use the dimensional values with the TDB file and the BCC and the CRFE. It is there already. So and okay, there are large time steps and save time. So in smooth right now it is disabled here, but that will be enabled further down the line during the development. And so this gamma parameter we are not going to take directly in the model for this model, so we are going to leave it as it is, and the periodic boundary conditions are going to implement it, and the cube filling. So as I'm mentioning, though we are going to do a spinodal decomposition with a random microstructure, but yeah, down the line the streamlining this GUI, just proceed whatever is there and track progress. So I would like to see here the capacity, which is the gradient energy coefficient part in the Cahn-Hilliard equation has given in the dimensional value, and we enable the spinodal and the TDB flag is enabled, and TDB name is given over here. This is the same TDB file which I have demonstrated previously. So this the forking of the solver to multiple levels can be done in the future, where whether you want to use a scaled composition or the dimension, or whether you want to use a TDB file, or whether you want to use user input Gibbs energy expressions, or you have any other form of expressions. So those things can be forked further down. One thing which you have observed previously, where if you keep isothermal case or if you keep non-isothermal case, the temperature conditions are enabled during the solidification conditions. Similarly, we can we have plans to do further down in the similar lines. But anyway, as I mentioned previously, you can always use a in file where you can edit the values manually. So these are the atomic modalities which I am going to give the dimension values, and this is the composition which I am going to choose in the alloy system. So with this, I should able to generate the file. So I'm going to give a run 2 and output file names as run 2. I'm going to generate in the demo runs folder itself, so which is not going to get affected much, so because we have given a different name. So before running, I would like to emphasize on the Gibbs energy writer, where I would like to show you manually how it can be done, similar to the KKS OpenCL model where we have used. But in the future releases, these information will be pipelined so that a user may not need not to spend time by himself over here. Again, I'm going to use the Python to read this Gibbs energy, to execute this Gibbs energy, which is the input.in. So that file is not over here. So let me copy to avoid all these confusions. So in file, cp in files, in file, so let me check files, cp input, put st over here. Yes, now we have that in file. What I'll do is I'm going to use, so you can generate a we will implement this in the GUI also. MicroSim, sorry, what Gibbs energy and the input file, st. So similar to the previous expressions demonstrated, so it is going to take into the account of the phases, and it will see this is actual. So as Professor Abhi mentioning, so the PyCalculate is it's in different form which we may not able to port it into our models, which through SymPy CodeGen, which we are going to convert these variables into as a function of y. I mean, this is going to be this array is going to take which is the element we are going, it's first element and second element. So that transition is we are going to make, and calculating the derivatives wherever required, and similarly it is happening for this. So one thing I would like to mention is the components which we are going to use over here. So the in interstitial items, so this is the sublattice information is essential, but it is already inbuilt in the TDB, so which user may not need to worry, that is taken into account. And so after this I am going to click run. So it is executing. So let us check what kind of microstructure it evolves. So it evolved at 0, which is also a random. I have used a very small domain, which is just 64, because one thing I would like to emphasize is, rather I'll open the close terminal. Again I'm paraview, so which is going to show, sorry, it is showing always run 0. Let us check. So sorry, the run 2, I think we have given the save time step wrong. Let us cross check. Oh, this is very high. Yes, let me keep 100. So let me generate again. So let it overwrite and let's run again. So it is a small system. We can give it try to rerun and preview in paraview. So it has generated. Sorry, and apply. Yeah, it is evolving. Microstructure is evolving. So this I would like to demonstrate. We can use both user defined functions or a simple parabolic function or the actual Gibbs energy functions representing the free energy function. So one thing I would like to highlight is the difference in using the thermodynamic function or the second order polynomial. So the computational cost which we have to account here is if you start using the actual thermodynamic function, you have to account for calculating the logarithmic terms, and the computation cost in doing so it is very high. So it's a trade-off, but you can, as the methodology always any mathematics can represents any physical phenomena. So it's up to the user choice how they are going to go forward. And after this I would like to show one more where the precipitation is being studied, for which both Cahn and Cahn-Hilliard equations are solved. I'm going to choose again n file which is existing for this solver Cahn-Hilliard model, and the solutions were also on the implementation is also on the FFT for this model. And in files I'm going to take this, so I would like to run through them. So let us check one thing. Yeah, domain filling was done with cube, probably which we would like to make spherical, and seed which is cylinder option over here, and center point I'm going to give, I think this was given 512, I'm going to give it 256, and the radius around 20 grid units. Save, and I'm going to delete this. Next, so Cahn-Hilliard model, I'm accounting, say all these parameters are loaded with the scaled values of 1, and I'm disabling the Spinodal here. You can see that you can disable Spinodal, and also right now I'm going to demonstrate only with the TTB flag as 0, and further developments we can make TTB flag 1 where it can solve for both also. And then so the scaled values are taken, and we are going to take, instead of 0 for matrix, we are going to take supersaturated matrix, and then I am going to generate the module in file run3, and run3 output is also run3. So to keep track of what we are going, so you can give a name of your convenience. I have to generate the files, so I'm going to generate these files in the same place as the demo runs, and I'm going to save over here. So those files are generated, and I'm going to run. So the solver is creating the input output files. So let us see with a preview and apply. Oh, sorry, yeah, okay, I have given a wrong input, but you can see the clear implementation of periodic boundary conditions but my initial CD is wrong size, I mean the wrong location. So probably we can account it. Just we can go back and let's see what the domain says. 256. In that case, I should give my radius of this is 128. So that is there in the corner. So that we can see clearly. 128, 128. I'll use 20 grid points. Save, and I'm going to delete this right now. Next, yeah, I'm going to save it as 4, run 4. So as Professor Avik mentioning, so this in-file generator is very handy when you are creating your input file or making a test run. Once you generate your appropriate in-file for the solver and appropriate in conditions, if you want to do any parametric study, you can use the batch scripts which can be developed through batch scripting package language, which can be ported onto HPC clusters easily. And then preview. You can see something is happening. It is evolving. Let us open documents and demo runs, and this was run 4. So run 4 files you can see here. So you can see it is evolving. So the growth that we can observe. So one thing I would like to emphasize, so most of the times the solvers takes the input, but we should be very cautious in choosing the material parameters, the dimensional or non-dimensional parameters, including the time step and the grid size. We have to account for we are not deviating too much from the physics of the problem. With that, I would like to conclude this session, and I would like to take questions.
A very good demo.
Yeah,
Mohan,
thanks, Mohan. Very nice demo. Yes.
Very nice. And also I want to tell that whether people use FEM in Abacus or ANSYS, I mean, everywhere it's always there that one should watch out what numbers they are feeding in. So that part will remain always for every software. And I think we are going to have some example in files and the outputs as JPEG files for the help, as a help for some newcomers.
They're already there.
They're there one set. We may expand that for various other options, so that the newcomers will have adequate help to choose some sample runs already, and then they can go on to expand them for their own cases. So all that will happen. So yeah, I hope the students who are attending have seen this live. The runs are actually live, so they are actually calculated live. So if you have a powerful computer yourself, you can even run bigger ones. And of course, if you have NSM facility or a cluster facility in your university, you can run even huge. So I hope it was useful. Yeah.
And adding to that, Professor Fani, we can leverage, the students can leverage with the GPU solvers if they don't have access to clusters. So any GPU can do a better job than a good cluster, I mean the basic cluster.
Yeah. So we have some metrics to show that roughly a 20,000 rupees worth GPU can give same performance as 16 CPU cores. I mean, this is a work that came from Gerald and Mohan. So if you have a workstation worth about 1 lakh or so, it can already do fairly good computation. Yeah.
So any questions for Mohan?
Narsimhan has raised his hand.
No?
Narsimhan.
Yeah, I have a general question on the not exactly on this on the Cahn Hilliard part, but on the general thing that the first talk that Abhi gave. So in the general formulation, when you have multiple phases, then you have to enforce this constraint that the summation of all the phases equal to 1, right, at every point.
Yeah, so Narsimhan, there are several possibilities there. So there are multi-phase formulations which treat the order parameter as a volume fraction, in which case you will have to do whatever you are saying. There are also formulations which treat the phase field as a really an order parameter and not as a volume fraction. And therefore, there are formulations where you will not see the summation equal to one constraint being applied. Okay, so both formulations exist. The one formulation where the volume fraction is 1 is what I have adopted in the grand potential formulations that I showed you. So, and that allows you to interpolate, use that as an interpolation function for anything relating to energy or composition or anything. So that becomes a natural choice for
there is a Lagrange multiplier that will be there in the formulation.
Yeah, we have.
So so now for whatever reason, suppose I want to print out, say, the chemical potential,
right,
or the free energy functions, or the Lagrange multiplier as it is evolving, as the solution. Is that possible? Do
we don't calculate and print out so much. So it's something that we avoid doing as part of keeping the computational more efficient. But if that is absolutely necessary, we can put it as a flag. Because chemical potential is directly input. Chemical potential is directly an output because it's a file that I write. Yeah. So chemical potential. Yeah.
I think I missed what you said. Did you say that you could print out the chemical potential if needed?
Yeah, chemical potential is already printed out in my module because I'm solving for it.
Oh, okay. All right. So that is also one of the output variables that comes out in parameter. You could just pull down and plot that as well.
Yes, exactly.
Okay, fine. All right. Thank you.
But not in all modules. So
you can. So it's essentially the. So for example, the variable that you are solving for. For example, I solve for mu. So it directly gets. But I can also write composition. There's a write composition flag in my in file. If you turn that on, it will write both composition and chemical potential. So you can see both. So the other solvers work on the composition field. So they will write out composition as a variable, as an output. But they can also, we can also think of including a flag, right? Like I have for write composition, write mu. So they can compute the mu and write it out correspondingly, like my solver. So yeah, that we can adapt and use.
Or we can push it to a post processor because sometimes these are really costly.
Exactly. There's memory. That's why we want to leave
it
as a flag.
Basic composition and redo the calculation in a separate code.
That's typically what I do for my stuff as well. So if I require composition, I'll just rework it from the outputted mu files. So.
Okay. Gotcha. All right. Thank you.
Any other questions from the audience?
So I think I would like to. There was a previous question regarding the CUDA and OpenCL. Shall I comment on OpenCL part? I think
the installation. Yeah. Somebody wanted installation help.
So there is one runtime library from Intel, which you can go directly download. Even I think it can be downloaded for the end user without any payment. I think without any subscription. So that can be used across all the platforms. That is what I was using. I was running it in Linux. I was using it for a cluster where you have to use OpenCL and CPUs. I was using it in a desktop, and I'm using it inside my VirtualBox. And also in Windows, you remember the Windows 10 has a Ubuntu terminal feature. So I was able to use the OpenCL header files and that runtime library inside the Ubuntu terminal, where it allows me to compile and do a test run. So there is Windows version also is there, but I didn't try. So this is so much cross-platform compatible. So it comes with overhead where the other things, runtime libraries should be taken care accordingly. And regarding the TDB files, there are repositories like NIST and NIMS where they documented the TDB files which is available in open literature. Sometimes what they do is the publications just they give the data values of the parameters, but they took efforts in compiling those data and making a TDB file. So if you don't find the TDB file, you have to make a TDB file. So it's always so if you are not willing to take a TDB file, if you write a simple form of expressions, you can write it, and with that module we are going to introduce where user can give the expression.
Yeah. So that is something that is under development. We will be having that as well. Yeah. Very soon.
So the forkings in every solver can be taken. So for example, this goes to multi-component, multi-phase, 3D, and then elasticity. And
so that will not be a forking. That will be a generic development. So all solvers will become multi-component, multi-phase. So that will be a generic feature. The forking will be essentially with respect to how we treat different things. So for example, whether we do function calculations and which functions we use for the energies, and whether it's a parabolic expression, whether it's ideal solution model or a regular solution model or a user-defined function or a TDB function. These will be the types of forkings that will be.
Yeah, good.
Okay, doesn't seem like any other question. By the way, everybody who Ram, you have a question. Yes, Ram, go ahead.
Hi. So besides the numerical advantage you had exhibited, so the tutorial also has a bunch of literature reported scientific benchmarks which you can reproduce with this. Is it?
Yeah. So that's one of the plans. So one of the plans that we are having, we'll be benchmarking. So for example, we'll be taking a given problem and address it with different solvers, and we'll showcase that all solvers give us the same result. Okay, that's one sort of benchmark. The second benchmark is essentially if there are analytical solutions available for the problem. Let's say you have dendrite velocity calculations from theory. We will be benchmarking against that dendrite shape calculations, for example. And so we'll have benchmarks against analytical solutions wherever available, and benchmark cross platform against different solvers wherever available. So this benchmarking could also be against multiphysics solver libraries already available. So this will be once we are fairly ready in the next 6 months. You can see a lot of benchmarks being posted.
Sure. I mean, especially regarding the various inputs which you are feeding and whether you are on the right track. So if there are guidelines on these kind of benchmarks, then maybe those could be starting points to sort of play around with.
Right. So these infiles that you are seeing are already because of problems that are well studied. So these are already well studied infiles or well studied problems which we have ported along. So they are already good starting points. We know what the right result is and therefore we know whether we are getting correct things. But extensive quantitative benchmarks is something we will post along with.
So for example, Ram, I'll tell you, elasticity driven precipitate growth problem. Rajdeep and Guru, they have a paper with Abhi. So their solution, when Tushar developed this code, we have already benchmarked and we have looked at also Johnson's solution. So that type of benchmarks are already there with us. Some of these things we have done. That's why we have given these examples also. That if I take these parameters, whether I get back the analytical solution. Correct. That was one of the.
So essentially, what he's telling is as a posting. So you can post the solutions and the benchmarks as a report that this is what the solution was.
Yes. That will be done in the manual, and we can also put the analytical solutions in some Python file.
As a formal benchmark.
Yes. So it will be like a Python file, and then you generate your result and just extract some data and see whether the analytical solution and this match.
Right. I mean, you can already post that and match it and post it. I mean, we don't even, the user can use the Python script, but even the posting of what the analytical solution is and superimposed on the actual solution would be a nice start. Posting on the repository, because then people will already know, he will have already confidence that this is solved.
Yes. We can do that.
Thank you.
Abhik, I also had one generic comment because these questions came from Narasimhan and we are also using CalFAD.
Right.
When CalFAD database is developed, it comes from the specific hits most of the times. And it is not very clearly spelled out whether they separated the elastic part or not when they calculated the free energy polynomials.
Right.
Those are all fitted polynomials.
Even though the polynomials are taken, they don't use the gradient energy coefficient, for example, consistent with the same model that is used to develop the free energy. Because there is a way to, at least in solid-solid transformations, connect the coefficient to the gradient energy coefficient to the free energy.
Yeah,
so,
but I don't think that is done in the.
Yeah, so I mean, what I'm trying to say is that for the interested audience here, there are also research problems. Even though we are saying that we are not posting research problems, it is worthwhile to think about many problems using MicroSim. So
Yeah. So what the point is, we give TDB as a feature. Okay. So anybody who has a TDB can run it using that and get results, which might be immediately useful for some users. But for the users of the type that Guru is just talking about, essentially who are more interested in the actual physics of how a TDB comes, with the correctness of it, whether it is actually the right way of doing things, we will be adding features where you can write your own functions, for example, and generate those functions and utilize, but the same platform to do the same studies. So the platform remains the same, and we want to give enough flexibility for both types of users who just want to input something and get out for some usage, and types of users who want to do research with it, academic side. So both are possible. Krishnan.
Yes, actually, you can use. So you are. So there is a question in the chat box, Krishnan. I think it is directed to Mohan, but I can tell you that if you use a sustained noise and if you use in your Cahn-Hilliard equation or Allen-Cahn equation, you can actually mimic nucleation. In fact, you can mimic the Johnson. See, please understand, JMK itself is a fitted the equation. So basically, studying nucleation, it's a see the nucleation, classical nucleation matching the R star and stuff. That is not a very big problem for you. The problem is the rates, but the problem of rates is that you don't even know what is the correct.
Yeah, so just to answer the thing more quantitatively, it is, this noise parameter, you can put very artificial noise. It will give you a lot of nuclei and maybe even nuclei that makes sense when you compare it with your experimental results. But that might be physically incorrect because it might be adding energy to your system beyond what is. So it might be shifting your equilibrium compositions to that level. So one must be careful when you are putting noise. And this noise, incorporating noise in phase field solvers is actually best discussed in papers from Granazzi and Tamas Puzzai. They discussed this very carefully in terms of how the noise amplitude has to be decided. So I basically request you to read that whenever you want to input noise into your phase field models, particularly for incorporating nucleation or affecting nucleation. But qualitatively, you can actually generate many microstructures which are routinely seen in experiments just by putting these type of noise. But the physics, whether it is actually correct, it has to be explored a little bit further. Okay. So
in this context, there is a recent paper where they are trying to match iron chromium spinodal from the phase field. So in that process also, they realized that they have to actually do some Monte Carlo kind of simulations, because even though we think of it as noise, because of the interactions, that noise has its own feature. And if you don't get it right, you don't get the microstructure right.
Exactly, so if you want to do it the classical way, you won't want to listen to it. You have to solve something like the Fokker-Planck equation and get the amplitude, and you don't want.
So that is the right way, but yeah.
No, but there one very important thing that I will tell you, because I have practically faced this problem. You have to go to really large system sizes, because you remember that the noise has to be truly.
The scaling is with 1 by delta x, 1 by delta x, delta y, delta z.
Yeah, so that is one thing. And second thing, as all of us know, it has to be a perfect white noise.
It has to be white noise, and exactly, and it has to be not having any bias. Otherwise, you will get absolutely not.
So that is one very bad thing that happens. That if you add noise which is colored, for example, I have seen a lot of people using uniform noise. What happens is that in such cases you will suddenly see huge amount of nuclei. All these are unphysical.
Yeah, and all of it is unphysical. So.
So
noise is a careful term, and in phase field community, people are always, if you know how to tame that horse, you can use it well. But if you don't know how to tame that horse will run over you and give you very bad results. So that's the whole point. you will fall down.
One good thing about MicroSim is that since people can now use very large system sizes, if they use white noise, now the scaling that 1 by delta x delta y delta z, now that will not affect. Otherwise, if you do exactly the fluctuation dissipation theorem way, you will see that in your previous system sizes, like I had 512 by 512, I'll see two nuclei.
You become correlated noise. So basically, you will have noise seeing noise each other. That's why it will not work.
No, otherwise you will have two nuclei finally.
Exactly.
The entire box.
Right. Exactly. So. Yeah, so as a message to the community, noise has to be handled very carefully. Okay, that's
right.
Thanks, Gerald. Has a comment.
Gerald has a comment. Where is Gerald?
Yeah. So the right response is thanks.
Okay. Yeah, thanks, Gerald. Yes, absolutely. No, I mean we should thank the NSM people who actually funded it. So.
Yes.
Because as a practical user, we have been searching for a hordes of softwares. And
right. And this is essentially, not only for the practical user, also to, consolidate all the knowledge that we have in the face field community in India. See, unless you consolidate like this, what we felt was you keep reinventing some of the things, and which is not really in the best interest of the particular face field community. So this is in the effort to basically consolidate and thereby make things more usable for the user community at large.
Whatever the softwares that you have flashed in the morning, right? So all of them you have tried it out. So and then we dumped everything and started writing on our own.
Right. No, I mean moves and prisms, they have their own very bad limitations. You just can't run them on large sizes. And if you want to write your own code there, it becomes so much overhead in terms of learning their stuff. You don't want to do that. So multiphysics solutions, we recommend only when you have a specified model in mind where you really want to explore the computational intensive nature of the solutions. It's there where you explore that. Otherwise, you must look at multi-phase, a particular phase field solution if you want generally.
Agree.
One request to the participants who stayed together all the while. Please don't forget to give your feedback, because our next event from the team will depend on the feedback you give, and we want to make sure that our events will be very useful for you to take these kind of programs for your usage and also for contributions from your side also. Yeah.
So by the way, the recording, we will post it at some place where you can we'll share the link as well. So all of you can access the recording whenever you wish.
NSM will not post it in CDAC side.
So we will request Satish for a repository. They were talking about posting our solver itself. So we'll ask them in the national repository, they have some space. So we can post both our solver and the recordings of the workshop.
Yes. And then they give us more computational time.
So, I mean, Satish, the whole idea is to, be in the good books of the NSM leaders, so we can have extended funding for our prospects, our projects.
But I think NSM has now one good thing, that for students who are studying in IITs, NITs and all, they are going to give a lot of they are giving a lot of training. So NSM is organizing a lot of training on GPUs, CPUs, MPI
that's
and all
one of the things that they are taking up as training exercises.
Yeah, so that way, a lot of people who are attending, for example, they will also know the nitty-gritties of the systems on which they have to run and stuff. So they are already getting trained on all the machines that are there in ISC, IIT Hyderabad. Today it started.
Right. So also, I also mentioned this before. We can do one thing. We will post along all these scripts for running on these machines. So anybody who wants to access these machines, they can.
Yeah. So the NSM facility specific scripts can also be made available. I have just now posted a link in the chat, which is from the NSM Center at IIT Madras. The IIT Madras one is basically a nodal center for training in HPC and AI. So there are many workshops, And I request the audience to bookmark, because there we will see upcoming workshops lined up. So right now, I can tell you that in February there are 2 workshops, one on GPU programming with CUDA and GPU programming with OpenACC. So bookmark and join them, and then you can learn also from the NSM events from here. Yeah.
So I was discussing with Abhik also. So basically, students who are there, if they want to become developers, maybe we can create an alpha branch or something where they can learn all these GPUs and CPUs, and they can also pose their interesting problems and solutions using MicroSim.
We can do that. Yeah.
So, because ultimately we require not only users but also developers.
Yeah, I mean, no, I think this is this. I think users, we want to expand the user base as well as the developer base, as well as we want everybody who came for the workshop, we consider you as our team. And
and also more importantly, it should not take somebody to do a PhD to be able to do a phase field simulation.
Right.
So we want to make it easier to get in.
Right.
Yes. All of us have done.
I certainly
have done a lot of coding. So we have done so much coding in our PhDs that today I don't think everybody should suffer the same way. We are sharing it, so you can start doing it. Yeah.
No, everybody should suffer the same way, but by contributing to this code.
Okay, good.
Yeah.
So I think it's a good day. Shall we
So
call it a day?
I think we can effectively close it. So
yeah, normally there's a Thanksgiving and all. Hey, Narasimha, you have some question there? I see the hand is up.
Yeah, I think
Just go ahead and ask. Go ahead and open the mic.
He didn't lower the hand. That's all. He asked the question.
Okay, fine. Yeah. So yeah. So because the others who have spoken shouldn't be thanking themselves. So on behalf of the rest of us, I thank the speakers who have given excellent demos, live demos, and I hope it was useful for all of you. And we look forward to the next event. And if some of you have already tried out, then you can make more out of the more specific workshops that we will be having in the future. Yeah.
Right. Okay. Yeah. So with that, we can close
it.
No, we can see we can just close it, and I think our presenters can have a short meeting amongst ourselves.
Yeah, yeah.
We can just stay on this link until everything.
Okay.
Okay. So we close the talk. Yeah.
Right. We close the. So thanks everyone for attending. Very thanks for this first workshop we are having. Thanks everyone. Yeah. And for the interesting questions and the participation. Yeah.
Yes. Thanks a lot.